Welcome, everyone. You are joining us for Optomechanical Techniques for Optical Compensation of High-Performance Imaging Lenses, presented by Optikos and hosted by Photonics Media. Today's speaker is Nathan Wallace, Director of the Engineering Department at Optikos. Nathan joined Optikos in 2014 as an optomechanical engineer, contributing to the design and development of complex optical systems. We're also joined by Rick Skoglund, who will start off with a few words about Optikos. Rick leads industry outreach and brings a strong background in both mechanical and biomedical engineering, helping bring Optikos' optical expertise to the wider market. A quick note, feel free to ask questions in the chat at any time. If you experience technical issues, try logging out and back in. You'll receive a link to the webinar recording in your inbox after the session. With that, let's welcome Nathan Wallace and Rick Skoglund.
Thanks, Haley. Good morning, afternoon, and welcome. We're excited to have you join us today for this special session. Before we dive in, a quick word about Optikos Corporation. We've been in business for over 40 years and been a leader in optical and optomechanical engineering, helping companies turn complex optical concepts into reliable manufacturable products. We combine deep expertise in optical design, systems engineering, and metrology with hands-on experience developing instruments for markets ranging from consumer imaging and industrial sensing to aerospace, defense, and medical devices. Today's webinar explores how optomechanical compensators can efficiently recover lost performance while supporting robust, repeatable manufacturing processes in modern imaging systems. And now, without further ado, I'd like to pass the floor over to Nathan. Thank you.
Thanks, Haley. Thanks, Rick, for the introduction here. I'm Nathan Wallace, and we're going to be talking about some optomechanical techniques for compensating high-performance lenses. So we'll jump into it. Just an overview of what we're going to talk about today. I'm going to do some brief details on optical compensators. I want to be upfront about this. I'm not going to go into the gory details of how you design for optical compensators. We're going to assume that our friendly neighborhood optical engineer has put together a design that has compensation in mind. And we're really going to look at the optomechanical techniques here. I will use an example of an optical system, show you which elements we're going to be using for compensating. And then we'll get into the details of what an external compensation mechanism looks like and what implementation of an internal compensation mechanism looks like. And then we'll have some closing remarks. So what are optical compensators? These are any adjustable optical element that you design into a system to help recover performance. And I want to highlight that compensators are not about making a really bad lens or a lens that does not pass spec into a passing lens. This is really just recovering some of the performance that is lost due to alignment, manufacturing errors, whatever other non-idealities are in that lens system. What's interesting about optical compensators is that you can design them in a way to correct for specific aberrations. Those could be coma, astigmatism, etc. Why are these compensators needed? You may say, hey, wait a minute, I've already toleranced my lens system. I've done a Monte Carlo analysis. I got really good yields. As long as our friendly optomechanical engineer puts it together with the right centration tolerances, the right D-space tolerances, the right tips and tilts on the elements, I should be good. I have this distribution of results that show that, hey, 90% of my systems are going to work. Well, optical compensation is really about that performance recovery. So you could take a lens that is on your distribution, but maybe it's on the lower end of performance. With a little bit of compensation, you can turn that lower performer into a higher performer. What's really nice about this is that this optical compensation can help reduce the system-to-system variability. So if you're producing some really high-performance lenses and you want to help skew that distribution to have a lower system-to-system variability, having these compensators designed into the system can be a great way to achieve that. I will highlight that not all systems are going to require compensation. You may do your Monte Carlo analysis, you may do your optical design, and you may say, I probably don't need these compensators. if you look at it and still design it into it, it helps reduce those build risks and enhance your optical performance. If something goes slightly wrong during your build, now I have this option to be able to compensate. So let's take a look at an illustration here of what is an optical compensator. On the right-hand side, you can see this is a reverse telephoto lens. I just got it from the ZMAX library just for the sake of an example here. And what's interesting is that, if I take the rest of the elements that are inside this lens and I move them around a little bit in X and Y, so I no longer have a nice rotationally symmetric optical system, sort of simulating how I would put it together with real world tolerances. If you look at the plot on the lower left-hand side, this is the resulting coma. This is over field of the system. And you'll notice right away that if I look on axis, I see that there's coma there. Knowing aberration theory, I should not have coma on axis. That is less than ideal. But if we laterally displace element 1, that can be an effective coma pusher for us. And we can actually null out the on-axis coma. So after I push that element around laterally, I can recover the performance, push that coma 0 point onto the center where it is, where it's ideally supposed to be. Likewise, I can take the last element, element 6 here, it happens to be a doublet, and I can laterally displace this for affecting astigmatism. Now, what's interesting here is that astigmatism on axis, I would be able to null it out, but sometimes these compensators carry some other residual aberrations with them, which really means you might have to iterate a little bit between pushing one of the elements and then let's say you correct a lot of the astigmatism, and lo and behold, you have a little bit of coma that comes on axis. You might need to adjust your coma pusher. So I just want to note that sometimes these things are coupled, and I'm not going to get into the optical design of this, but we're going to assume that our neighborhood friendly optical engineer has designed a system that has this performance recovery in mind, and that the first element and the last element are going to be our compensators. So how do we need to move these lenses for compensation? As an optomechanical engineer, what do I need to do? So in a lot of these cases, the motion for compensation, it needs to be very deterministic. It needs to be very precise. Well, what does precise mean? The precision requirements are often going to be in the single-digit micron range. We're talking about nulling out aberrations here. Very important for us to have very, very precise fine motion. And there's a few architectural choices that we can look at. There's sort of the external architecture, and there's the internal architecture. And what are we measuring when we're doing compensation? Typically, these are taking place in front of an interferometer. It's very easy to set up an on-axis system, do a transmitted wavefront error on your interferometer, get a look at what the wavefront looks like. What's great is that you can actually separate a lot of the aberrations. Use your Zernike polynomials, things like that. You can take a look at individually what are the contributions for, say, coma or astigmatism or other aberrations that are important to your system. On-axis performance is very easy to evaluate. And if you're going to be looking at, potentially some field balancing or off-axis balancing, you can also do that in front of an interferometer. The setup gets a little bit more challenging as you have to swing off axis, so rotate in front of your interferometer. You can also use an MTF test station for the field sort of performance, that off axis balancing. You really want to take a look at 2 field points that's equal and opposite and try and balance out the those aberrations. So let's jump into the optomechanics here. Let's talk about these external lateral compensators. So here's an example of an external fixture. The idea behind the external compensator is I know I have a lens assembly. I want to move a particular element. It'd be very convenient for me to put the compensating element in its own subcell and then have a fixture that can attach to the lens assembly that provides all the necessary inputs for the actuation, the feedback, those sort of things. In this particular case, we have some fine adjustment screws that are applying our motion. And you may notice that there are some digital gauges that are on here that provide motion feedback for where we've positioned this lens. I don't go into a lot of detail here, but I really like having some mechanical gauges on compensating lenses. That way I can zero out my system when it's in front of the interferometer. And as I make adjustments, if I ever have to get back to my starting point, it's very easy for me to get back. I just go back to my zero position in X and Y. So with this architecture, how do we start thinking about compensators? Well, take the example of element 1, which would be our coma pusher. We know we need to move that laterally to affect coma and null it out on axis. So we're going to go ahead and install lens element 1 in its own subcell. That subcell is then going to be attached to the rest of the lens assembly. So we have a lens barrel with all the other lens elements that are in there. We're taking this cell and we're attaching it to the front there. That affords us the opportunity to be able to shear that with respect to the lens barrel and make those lateral adjustments. If I take a look at our external compensator fixture installed on our lens barrel with element 1 here, that's what I've depicted. So element 1 is on the top here. The rest of the lenses in the lens barrel is on the bottom. I have truncated it so it's pretty clear to see. But if you look at the center section, this top element that is here, that is our compensator element. That is located in its own subcell. Wrapped around this and supported and attached to the lens barrel is our compensation fixture that has all of the mechanical actuators and things that we need to be able to nudge this lens cell in X and Y. So I'm going to zoom in. Here's some of the pertinent optomechanical details of this external adjuster. I have foreshortened it here, so we've removed the lens cell that's in there just to zoom in and highlight some of the features of the optomechanical implementation here. Starting on the left-hand side, there is a return plunger, a spring plunger. This is providing a restoring force to our actuator. I really like this as opposed to having two opposed adjustment screws where you have to sort of push and pull and fight each other. This is very nice to have sort of that spring-loaded return. Helps with deterministic adjustments. Now, if I push my cell to the left, it will compress that spring plunger. If I unscrew my adjuster and want my cell to go to the right, that spring plunger will provide that restoration force. Over on the right-hand side, you can see that there's a knob all the way over on the right that has a bushing, and that is one of the pretty standard optomechanical fine pitch adjustment screws. What's interesting here is that you'll notice, hey, this is a ball end adjustment screw, pretty common, but it's not actually interfacing directly with the lens cell. There is another intermediate mechanism in between. And what this is doing is there's a linear bushing here that provides sort of linear travel only for this actuation plunger. There's a little light return spring in here just so we can install it and it gets out of the way and we keep everything in contact. But really what's happening here is we are making sure that the ball end of the adjustment screw is not interfacing with our cell. And we are not imparting any sort of torsional forces or anything on that cell. And what's important here is that there are flat contacts that are contacting this lens cell. A lot of people will say, hey, I have this adjustment screw. It's got a ball end. I'm going to have that contact my cell. That does work, but flat contacts can aid in providing a little bit more precision. What does that look like? Well, these flat contacts help avoid coupled motion. So if you look on the lower left-hand side here, we have a spherical contact on an outside diameter. So we're imagining that this red circle here is our lens cell that we're going to be pushing in X and Y. I have on the bottom here this little black circle that's simulating our spherical contact that would be on an adjustment screw that is contacting in the Y direction. And everything looks great until I go to move this lens cell in the X direction, which is defined by this arrow. When I add some motion here, I get some cross coupling. This lens cell, this ring here, is going to slide on that spherical contact, and I'm going to get some unwanted Y motion. So I've adjusted it in X, and I'm seeing a small amount of Y motion. If we have flat contacts, on the other hand, let's go over to the right-hand side. I can push this in the X direction, and because I'm sliding along this nice flat surface, this is preserving where that Y location is, and I'm not getting any unwanted motion. So for compensating lenses, this is really, really nice. I'm sitting in front of an interferometer. I'm looking at my Zernike polynomials. Hopefully, we've changed it from R theta to X and Y, so I have a really nice readout of, say, coma, for example. I have the X component, I have the Y component, and I have these orthogonal adjusters that are there. I can make a deterministic change to affect the X component of the coma and not adversely affect the Y component of my coma. A few more details on sort of the lens cell, how you implement this. It's not just, hey, I put a lens in its own ring and I'm going to bolt that onto the end of my barrel. There's a couple of little details that you may want to add just to add some precision there. One of those being some flat pads, where these are raised flat pads that are making contact with your lens barrel. This is important. It keeps it sort of quasi-kinematic. It prevents any sort of errors in having two large, broad, flat surfaces come together. Also, you may notice that there is a clamping plate, this sort of gray colored plate on the outside that is supplying the bearing surface for the fasteners to bear down on when this lens gets locked in place, presumably after we have achieved some compensation. So there's some details on this. If you think about, well, why do we have this clamp plate in place? Well, if I just had the lens cell, which is depicted in the center picture here, if I just have the lens cell, I don't have that clamp plate, and I go to put in my fastener, and I keep it lightly on there. I do my compensation. Everything looks awesome in front of the interferometer, and then I go to tighten that socketed cap screw. Invariably, you wind up with some unpredictable motions. That socketed cap screw could bite into the surface of your lens cell. When it bites in, as you're torquing it down, it could drag the lens in an unwanted direction. A small amount, we're talking micron level precision. Everything really matters at that level. And I think a lot of us have experienced, working in the lab. I just took this picture over on the right-hand side. I went into the lab and I said, hey, let me take a picture at some lab table equipment. And you can see exactly where those socketed cap screws are just biting in. And I think a lot of us have experienced, you build up a setup, you go to tighten a screw and something moves a little bit. And then you're playing the game of, well, let me compensate it in a direction that's not quite right, hoping that when I tighten it, it goes into the ideal location. So if you add this clamping plate mechanism on here, you can help substantially reduce any of the unwanted loading when locking this system in place. And I put together sort of this little example on the top here with these gray and red plates put together. We're imagining that the top and bottom gray plates here are earth. They're connected with these pins, just symbolically these lines. So they're earthed together. They ride as one. And the red plate would be our movable plate that we want to move, and so forth. So I'm afforded the opportunity to slide that laterally. And then when I go ahead and apply clamping pressure to that plate, I'm not imparting any sort of unwanted lateral forces. The way that you can implement this on a lens cell, that's on the bottom pictures that are here, you can simply put a dowel pin with a clearance around your lens cell. The dowel pin interfaces with the lens barrel. It interfaces tightly with that clamping plate. You may want to do sort of a hole in a slot configuration so it's not over constrained. But that way we can slide the lens laterally, do our compensation, and then when I go in there to lock this in place, everything is very deterministic. So this is a pretty nice way to have sort of a precise locking mechanism, pretty inexpensive, pretty easy to implement, and avoids a lot of frustration in front of the interferometer. So that's great for external sort of compensation techniques. What do you do when space is limited? Maybe you're not afforded the opportunity to have this really nice fixture that you can put on the outside of your barrel. Maybe there's some other issues. Maybe there's a situation where this is going to have to be adjusted frequently for some reason, or there's some downstream integration steps that have to happen where you're going to need to go back and do a little bit more tweaking of this optical system. Well, this is where sort of internal or onboard adjustments can be beneficial to a design. If you take a look at the picture on the right-hand side, this is a challenging geometry to try and get an external manipulator around. We sort of have this lens barrel. There's this monolithic flange that maybe it's mounting to a focal plane or mounting to something else. Very difficult for me to get some external mechanisms around this to be able to move an element. What can I do for this? Well, when you have sort of the tight space constraints, you can take a look at implementing some lateral compensators just internally. And some of the optomechanics that's involved here is putting on some adjustment screws. So maybe you tap your barrel, you have onboard adjustment screws. It is possible to sort of have a hybrid solution where you have some external components that bolt on, but you have a lot of your mechanics that's helping support this system. They're internal, they go along for the ride, they ship with the product. So let's take a look at an internal compensator here. If you look at this middle image, there is the doublet lens that is in here. It does conveniently happen to be on a flat annulus, so this makes it really convenient for us to move this laterally. If this was a spherical contact, maybe it's on a tangent seat or something like that, the lens would have a tendency to roll if I go to try and nudge it in X and Y. So sort of some things to think about. But what do we need to accomplish when we are looking at compensating? I need to be able to freely move this lens. I need it to be attached to the lens seat. I can't have it floating around in there. So I need some degree of preload to keep it seated, but I can't have so much preload that I can't move it. And I can't have it constrained in a way where if I go to push on it, I don't want to stress my glass. So the way to implement this is to use some flexure tabs that are integrated directly into the tangent spacer. I'll have some details on the following slide here. But essentially what that allows you to do is you can back off the torque on your threaded retainer, still make positive contact, still preload that element. And now I have the ability to use some external manipulators and adjust that lens in X and Y. And to take this a little bit further, I said earlier that I really like having mechanical feedback, some gauges to say, hey, where did I move this? Where's my zero position? How did I start? There are some port plugs that are in here, and you can thread on these little fixtures that attach the drop gauges. And now I can take my barrel, I need to go compensate it. I can add these little components to them, get my feedback, be able to do my compensation. So what does this internal compensator mechanism looks like? This is sort of your standard three-blade flexure lens contact. There's a lot of great examples of this in literature. But the only difference here is that we're using not only the flexure contacts to apply preload, but also we're carrying a hard-mounted tangent contact along with this spacer. So if I back off my retainer, I have the flexure tabs. Those are applying my preload. Once I move my lens and I'm happy with where it is at, I can then tighten my retainer and then go to the more standard tangent contact on my lens. I can tighten that. Now I have something that's firmly attached, and I'm not worried about having some sort of other load input into the system perturb that element, move that element when I have the very light preload afforded by these flexure blades. So with that, that's a sort of a bunch of details on how to implement some compensator techniques from an optomechanical standpoint. Just some closing remarks here. These compensators, they're a great way to maximize performance in a lens system. The compensators can help correct for those non-idealities. You know, I built something, maybe I got some alignment issues, or I need to target a specific aberration that may be present in there. I'm afforded the opportunity to make some optomechanics, move those elements around, recover that performance. If I'm thinking about sort of costs of systems and complexity here, external cost compensators are fantastic to push the complexity into the tool. So the mechanism is a one-time type thing that winds up being a little bit costly, but I'm not shipping it with each unit. I can still do my compensation, recover that performance, lock everything in place, and I'm not adversely affecting my per system cost. The internal compensators provide this flexibility when you have very limited space, but still produces that precision adjustment and the firm retention that you want for a product. I do want to highlight that these are not the only implementations of optomechanical compensators. There's many other ways to do this. I really wanted to highlight a few ways that has worked for us, and give you some inspiration and ways to think about moving lenses around and recovering that performance. And with that, I want to say thank you very much, and I'm happy to address any questions.
Great. Thank you, Nathan, for that great presentation. As Nathan said, we now have time for a few questions before we wrap up. If you haven't already, please type your questions and/or comments into the chat box. Okay, the first question I have here is, if you have a lens that has already been designed, is it possible to use these compensation techniques, or would you have to go back and modify the optical design for compensation?
This is a good question, and this comes up from time to time. So ideally, you want to go in and work with your optical engineer, design in some compensators to recover that performance. But what winds up happening sometimes is that you've designed a lens, you put it together, and you say, hey, you know what? I have an optical design, it's done, but I didn't really take a look at a coma pusher. I don't know what element to adjust here. A great way to sort of approach this problem is to take a look at what your most sensitive element is. So if you know, element 3 is that's my pesky element. It's my most sensitive. I looked at my tolerance analysis, my sensitivity, and that one is that really needs to be centered really well or positioned really well. That is probably the best element to go after for sort of this active compensation. Work with your optomechanical engineer, get a scheme together to be able to nudge that around. Now, you're not going to get the best results in front of the interferometer because you're going to move it and you're going to see maybe astigmatism goes up, coma goes up. Things are all sort of aberrations are coupled together, but it does allow you to sort of minimize aberrations on axis and potentially balance things across the field. So if you didn't have the chance to design the optical compensator in your system, you can still use these techniques to help recover some of that performance.
Okay, thank you. The next question I have here is, I can see how compensation could work well for a visible lens using an interferometer. How would you compensate an IR lens system?
That is also a good question. Yeah, this is, I think what I presented here was a lot of sort of visible techniques. What do you do when you have silicon and germanium and you can't see through it? There's a few ways that you can think about compensating. The optomechanical techniques are going to be pretty much the same. The real question is, what are you going to use as your optical feedback? There are some IR wavefront sensors that you could take a look at that would give you the wavefront information. You could also do this if you had sort of an area detector type thing that you can look at. If you really got desperate, you can take a look at an image formed on axis of just a spot. sometimes taking a look at what the spot looks like and moving an element around, you can do a surprising amount visually. Obviously, you're going to need a detector and look at it on a computer, but you may see some of the telltale signs of, hey, I have on-axis coma. It shouldn't be there. Let me make some adjustments.
Thank you. The next question I have here is, you discussed a lot of details about lateral adjustments. What about airspace compensation?
That's also a good question. I did not go into any details for airspace compensation. Maybe that could be a future webinar. But there's a lot of different methodologies for that. And if you think about the element one, sort of that lens cell that we presented for the external optomechanical compensator, that really lends itself to also have some airspace adjustments where I could take that cell off. I could put in, say, a nominal shim, a nominal thickness that's in there, do some measurements. Maybe I am trying to compensate for back focal length. Maybe I'm trying to compensate for spherical. Maybe I have a stereo pair and I want to get the magnification sort of just right. So putting in a nominal, doing a measurement, calculating what you need to change that and put that in there. But yes, there's many compensation techniques that you can use and mechanisms that you can use for doing airspace compensation.
Okay, thank you. The next question I have here is, how robust is it with vibration? Example, turbulences during fly transporting.
This is a great question, and the way I answer this is I like to add a lot of belt and suspenders. So how robust are these? I do a compensation. I laterally move a cell, and I tighten my fasteners, and I send it on its way. Well, there are probably some shock environments that maybe this is going to have some issues. So what do you do for sort of a belt and suspenders? I like to apply some fasteners as well as some bonding agents and mix the two. Maybe you liquid pin your systems together. In the case of the internal laterally compensated lens element, what wasn't shown there is that after you do your compensation and you're happy with it, you can pop that in place. So now I have radial potting that's helping constrain that lens. And keep it in place. And I also have the axial loading, again, belt and suspenders. But a really good question, things to think about. You want to make sure that your optomechanical implementation is going to be robust for all environments and use cases.
Okay, great. Thank you. The next question I have here is, what is the best way to create a single lens/element? Can be radial and axial compensator in the optical system.
Coupling the axial and the lateral together. There are a few ways to do this. I would have to put some thought into this. So I'd love to get an email about this. There are some techniques in literature where you can have some lateral adjustments, sort of like we have shown. But also you can make some axial adjustments. There's a penalty here, and I'll talk about it. But one of those is to have some lateral set screws that are interfacing with, say, a sphere that is in the axial direction. So as I tighten that screw, I can either push or pull that sphere in and out from there. I think this is used on old lithography lenses and things like that. The only caveat here is that when I go to make one of those adjustments, I have my 3 spheres of contact. I adjust one of those, I am going to tip my lens. So there's a little bit to think about there. Alternatively, you could think of maybe you have a floating setup that you're then going to bridge and bond or put on some other mechanics around that's going to constrain that lens in place. That's another way to do it, where I can make the adjustments and then I couple those together. But a really good question. I'd love to have that design challenge and put something together. So I appreciate the question.
Okay, great. The next question is, thank you for the talk. I noticed we talked a lot about lateral compensation, but not as much about tilt for optomechanical solutions. Can you speak about this a little bit, please, and your thoughts about spring lifetimes in your proposed solution?
Yeah, this is also a good question. Doing sort of tip tilt adjustments. Maybe you have a folded system, or you have a fold mirror in there, and that needs to have some compensation on there. I can remember a situation where I had a folded system, and the field tilt compensator was the fold mirror. So you got to go in and do a tip tilt adjustment. If you have an element that's very, very sensitive to tilt, then you're going to want to have some sort of tip tilt adjustment. As far as spring lifetime, well, it depends on how much of that stress strain curve that you're using. What is, if the spring is going to be on board for the life of the product, and it's in a compressed state, and it could have some other issues. What's great about the external compensators is that the spring lifetime is essentially, it's part of the fixture. You can do a preventative maintenance schedule. You can replace that. Things like the flexure tabs that were shown on the internal adjusters, those are sort of a one-time adjustment, or limited use case adjustment. It is sort of inferred that you're going to lock this in place. Maybe you're going to bond your element, and you're going to ship your product. So if you get some weakening of that flexure tab, it's not going to be super adverse. You'd also want to design around something that is going to either last for a long time, or not necessarily be in a position where it is going to be flexed to a limit or a point where you're going to have an issue. And if you find yourself in a situation where you're making an adjustment and articulating the spring, and taking a look at your SN curve for fatigue and things like that, you may want to look at some alternate materials for that spring. Maybe something that has just a longer fatigue life, things like that. Hopefully, I answered that question well. It's a very interesting one.
Okay, thank you. The next question I have here is, lenslets are manufactured with wavefront error, which adds up across the lens stack. Is it practical to assume that only decenter type aberrations will be dominant? Couldn't WFE render the interferogram too complex to recover the decenter caused aberrations?
Yeah, that's an interesting one when you have a lenslet array in there. So that would be a really cool thing to think about for compensating. I don't have a great solution, but that is quite a complex problem. And you're right, things are pretty well coupled in there. So trying to do a lateral adjustment may not give you exactly what you need.
Okay, thank you. The next question I have here is, I assume the flexure blades contact would be outside the CA of the lens, but would flexure blades scratch the lens, and is it a concern?
This is one of those things to be very worried about. Yeah, you certainly don't want to scratch a lens, and anytime you have optomechanics that's going to be contacting a lens, you really want to be outside of the clear aperture. I call it sometimes they call it the mechanical clear aperture, or the aperture of the lens that I can touch with mechanics. If it was kind of hard to see, but if you take a look at it, the flexure blade is run as a tangent. There is actually an angle that has been applied to that, just nominally, so that you get a line contact. You don't have the edge of the flexure contacting the glass. If I just had a straight flexure and I went to go push it onto my lens, I risk scratching. Another way, if you have something that is like really like has a very high degree of notch sensitivity, or you're very risk averse to having anything near that glass that could potentially scratch it, one option is to send your flexure tabs out for a quick forming operation, where you can just roll the end of that in a way that you've taken all those sharp edges and push those sort of away from the lens element. But a really nice question. Yeah, if I was mounting germanium with these flexure tabs, I would be very, very worried about scratching a very expensive optic. So a very insightful question. Thank you.
Okay, the next question is a three-part question. Um, the first part is, if the tolerance is of the order of microns, once you made the compensation with mechanical loading, how do you know you have achieved the compensation? Does it involve processing the interferometric data? And how about drift caused by thermal fluctuations?
Yeah, this is really good. So when you have this in front of your interferometer and you're making these adjustments, you make an adjustment, you hit your measure button, phase shifts your interferometer. I'm assuming you're using a sort of a phase shifting variety. Out pops your answer. You pull up your Zernike terms that are on there, and you can see, awesome, cool. I know what my coma value is. But as we all know from using interferometers, I mean, just heating the air with your hand around there is going to cause some disturbances in the fringe pattern. It may be worthwhile to do some averaging, which is pretty nice. So maybe take 10 average images, make an adjustment, take 10 average images, take a look at that. So if there's any air currents or other environmental factors that are in there. Thermal drift is a concern. There's thermal drift in the interferometer. Hopefully, you're in a lab situation where a little bit of averaging, closing the door, turning the lights off, that can help alleviate those. But then there's the real challenging issue, which is thermal drift that can happen just inside your lens assembly. Maybe you have there's a heat source or something else that's in there. I got some gradients. That is a lot more complicated to sort out, and hopefully with the design and analysis of your lens assembly, you've taken that into account, and sort of these micron level adjustments that's getting us into our ideal location, and that you have some headroom in your performance to absorb some of these thermal excursions that are going to happen. Hopefully you did a stop analysis, things like that on your lens. Again, compensation is to recover performance, try and push us into the more ideal performance area so that we're afforded a bit more headroom, so that we know that we're going to get passing units when it goes through all of the other environmental things and stuff that lens has to do.
Okay, thank you. The last question I have here is, what type of bonding agent is preferred to hold the elements in place? Well bet also minimize shrinking and unwanted stress on them.
This is a big debate amongst optomechanical engineers. There's many different ways that you can put these together. I really like sort of two-part, almost castable RTVs. I find RTVs can cure with relatively low stress. It's not like I have something that is a bonding agent that's got a ton of shrinkage. I put it in there, it's going to shrink. I got internal stress to sort of worry about. RTV is pretty benign. RTV is nice because it is compliant, which also helps for thermal excursions and things like that. It can be pretty robust. There's a lot of RTVs out there that are great for optics, and there's a few that are good for super low outgassing if you had a space flight application or something like that. So I'd really recommend, if you're going to be sort of bonding a lens element to a barrel, to consider looking at RTVs. There are other structural adhesives and things that you can look at as well if you need something a little bit more robust. So it's a really good question.
Okay, thank you. If we don't get to your question today, don't worry. We'll follow up with you via email. And if you think of something later, feel free to reach out to us at webinar@photonics.com. Before we go, I'd like to thank our presenter one last time, Nathan Wallace, and all of you for joining us for Optomechanical Techniques for Optical Compensation of High-Performance Imaging Lenses. This webinar was presented by Optikos and hosted by Photonics Media. Thank you all so much.